Tonight's topic will be connecting with the past, a timeline of astronomy history. This presentation goes a little bit longer than the 1 hour we have allotted, probably about an hour and 10 minutes or so. So please hang with me here. I'll try and get through the presentation as efficiently as possible. We've got a lot of ground to cover. What I want to do as far as the discussion tonight, I want to talk about the objectives for the presentation, show you and walk through the timeline of astronomy history, um, and then wrap up with a summary of our walkthrough of history, and then share with you references that may come in handy for you if you're motivated to dig further into the history of astronomy. So a little bit about our objectives, and I'm just going to move this down a little bit. There we go. A little bit about objectives for tonight. So what I want to do with this presentation is identify the main characters involved in the history of astronomy. I want to discuss key events and discoveries that these individuals made that put us on a path to where we're at today. Ultimately, what I want to do is connect the past to the present. For me, history is meaningful, more meaningful anyway, if you can uh, connect it to what's going on in today's world and get an understanding of why we're at where we're at. And hopefully, after going through this presentation, I hope to motivate further inquiry by uh, you, the audience here, to go out and do some research on your own. I always found history kind of fascinating, and I hope that you will too. And hopefully, this will be kind of a broadening out of your astronomy knowledge, so to speak. So that's what we've got. That's where my objectives for tonight are. Okay, and I'm not advancing. Okay. All right. Hang on, folks. Let me do this again. I think when I touch that toolbar, I run into trouble. So I'm going to keep my hands off of that. And we'll go to this slide right here. Uh, let's see. I can't roll that one. I'm going to put that up at the top. And okay. 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 So here we go. And I'm not going to mess with the toolbar anymore. So hopefully that'll take care of that. Okay. So here's our timeline of astronomy history that I want to talk about tonight. This presentation is going to be kind of a mile wide and an inch deep in order for us to cover so much ground. So uh, that is just kind of one thing that you can't get around given the time we have. We're going to start out around 3000 BC. Going to talk about astronomy and antiquity. We'll then pivot to ancient Greece and talk about the heavens being mystified. Um, when we get past uh, the Earth of Christ, we will begin to talk about the geocentric model perfected, and then talk about the heliocentric model that took its place during the Renaissance. In kinematic to dynamic, we'll be talking about Isaac Newton and Robert Hooke and their contribution to giving us a deeper understanding into the mechanics of orbital motion. We'll then get into a broader cosmos that really deals with William Herschel and how he expanded our reach and our understanding beyond our solar system. In a new understanding of physics and a broader universe, we'll talk about Albert Einstein and James or Edwin Hubble, excuse me, and their contributions that really set us on a path for the last 100 years, which I'm covering here in a segment called Exploration and Discovery Accelerated. So, in our first two groups of eras of astronomy history, we'll be talking about astronomy in antiquity and the heavens demystified. Throughout the presentation, I've inserted various other historical markers just to kind of give you an idea of when these astronomy discoveries and these astronomy principles were operating, and kind of relate it back to actual history going on. And as you can see from this one, we have a very Egypt-centric set of milestones, starting with the unification of Egypt, going all the way up to Cleopatra, uh, right near the birth of Christ. Um, and as well, just kind of showing you some of the rulers and accomplishments that happened during that period of time. Okay, so let's talk about astronomy and antiquity. And here we want to kind of kick off the conversation with Stonehenge. Stonehenge appeared on the scene about 3000 BC. Um, there is debate about whether or not Stonehenge is actually an observatory of sorts or not, or something else. Unfortunately, there weren't any written records from the time, so we don't have any definitive proof that this was an observatory. But some line of debate and discussion says that this was a funerary monument that included a celestial observatory, and there were stones that marked the rising and setting points of the sun at the solstices. So there is a hint just by the physical nature of the structure that astronomy was related to Stonehenge. Others have argued that it was a symbol of peace and unity. Um, Others have also argued it had healing powers due to the acoustic properties of the rock that constructed Stonehenge. So there are conflicting ideas about what Stonehenge is all about. But there is one strand of debate, one strand of argument that says it was um, astronomically related. When we get into ancient Egypt, we can really begin to see astronomy incorporated into the culture, manifested into the culture in a couple of different ways. Um, the calendar was developed in ancient Greece by the use of astronomy. This calendar, the Egyptian calendar, was used to set dates for religious festivals and fixing the hours of the night. Um, in a more mystical vein, the king's death was very related to astronomy. The Great Pyramids were aligned towards the pole star, which back then was a star, a faint star in Draco, as opposed to our own Polaris today. And of course, that's the precession. And we'll talk about the individual that discovered precession here in a bit. Um, the king's death, while being mystical, had a practical undertone to it. The idea behind aligning it with the pole star was so that the king's soul would rise to the heaven and become a star. And this is really to guarantee reliable flooding of the Nile and a bountiful harvest. The harvest of Egypt was very important. A good harvest would promote social stability and harmony. Uh, Poor or failed harvests could end up resulting in upheaval of the social and political system, which it had done on at least one occasion. So the king's death and his ability to get to become a star in the heavens was important. Obviously, the harvest was again a key feature, function, underlying need that the Egyptian culture had, and astronomy was used to determine the annual flooding of the Nile and synchronize planting and harvesting, etc. There was an ancient Egyptian god called the Hapi, Hapy, that personified the annual flooding of the Nile. He was that it was a symbol of a natural phenomena and annual rhythm, and it actually represented the order of the cosmos. So, ancient Egypt, we see a first recorded manifestation and use of astronomy for both practical and mystical purposes. In Babylon, around 900 BC, and I just want to preface by saying Babylon is actually a civilization that uh, proceeded and ran in parallel with Egypt. So it's an older civilization than ancient Egypt, but I wanted to focus in on their use of astronomy in this one particular set of bullets here. The Babylonians were alert to omens, and in our day, an omen would be a broken mirror, a black cat walking in front of you, something of that nature, and that would be a precursor to an unwelcome event. In the days of Babylon, their omens were more, they were like lightning, thunder, uh, even the odd chirping of birds. It could be discovering or finding sheep entrails and obviously comets as well. So they were alert to omens and actually compiled a list of about 7,000 omens. And then also, in addition to that, recorded a compendium or a listing of unwelcome events, which would include things like famine, floods, earthquakes, plagues, things of that nature. As they uh, refined their system, they incorporated into that their prognostications, astronomical phenomena, such as the movement of the sun, the moon, and the planets, so that if you had a planet in a particular position in the night sky, that may be a an omen for something unwelcome that might occur here in the near future. Kind of the classic example of correlation without causation, but it does represent a use of astronomy, but in this case, for what I would term mystical purposes, predicting the future, things like that. And again, these weren't things to be taken lightly. They're really the underlying driver for being able to do this was to be able to, um, predict events and create social and political harmony or maintain social and political harmony. So that's where we start out in our journey here with astronomy and antiquity. We'll now go to ancient Greece. And it was at this point in time that we really begin to see rational thought applied to the heavens. The four individuals that you see listed here are familiar. Certainly, Pythagoras and Pythagorean theorem, and his followers was one of the early contributors to astronomy, demystifying the heavens. Aristotle, a great Greek philosopher, Aristarchus. Uh, Not sure if I believe he was a philosopher, but uh, he definitely contributed to the knowledge and understanding of astronomy in a really big way. And then Hippa- Hipparchus, Hipparchus, I'm not sure if I'm pronouncing that right, but he was another individual as well that we're going to talk about. Um, the first three individuals were uh, born in ancient Greece. Hipparchus was born in Nicaea, which is in modern day Turkey. Okay, so what did these individuals do to contribute to our understanding of the heavens? Well, it was Pythagoras and his followers that actually came up with a proposed solar system model, model of our solar system. They assumed circular paths for uh, sun, the moon, Earth, and the planets, and they also assumed that the objects out in space were spheres, including Earth. They could pretty well deduce that from looking at the moon. The sun may be a little bit more difficult to do, but through a solar eclipse could probably deduce that as well. And then the five planets, although they were looking at those naked eye, they assumed those were spherical as well. You'll notice in this model, they're really focusing in on the solar system, and they really talk about or refer to the outer cosmos, the stars, the constellations. So really, it's just kind of an outer sphere of six stars. So there wasn't really a lot of thought that went into that portion of the sky. It was assumed to be fixed and constant. It did change with seasons, but nothing within the outer sphere changed. Really, the movement and the interest was in the solar system. With Aristotle, you have somebody that argued that again, celestial spheres were objects, and he also provided tangible evidence that the Earth was in fact uh, spherical. And he did this by observing lunar eclipses. And you'll see this picture in the upper right of the screen is actually an eclipse, a lunar eclipse image that I took a couple of 2 or 3 years ago. And you can kind of make out the uh, the curvature right here of the shadow of the Earth. And so this picture may not be the best, but it was that curvature and the motion of that shadow, or the not so much the motion, but the view of that shadow that led Aristotle to conclude that the Earth is spherical. He also deduced this by his observations of ships coming up on the horizon. He stated that first you'll see the mast of the ship, then the deck, and then the hull. And that gave him uh, the knowledge or the thinking or the the thought process that yes, this item, this thing called a ship, was actually coming up over a large sphere. When we get to Aristarchus, he employed eclipses and geometry to begin to calculate the dimensions of the solar system. So he was the first to kind of take a stab at arriving relative dimensions of the solar system. He concluded Earth is much smaller than the distances to the other objects, and that's pretty important. On the next slide, I'll show you his predictions or his measurements, and they're off, but he's going in the right direction, which I find to be uh, pretty cool. And then in addition, he had also invented a heliocentric or sun-centered model of the solar system. So that was he was way ahead of his time there. Hipparchus had discovered precession, which is the slow change in direction of the Earth's polar axis. So if you've seen in previous uh, quarterly presentations, we talk about precession, and it's really this circle that's made by um, the Earth's axis around this point, this point up here, and that's analogous or similar to the way you'd see a top spin when it's out on the floor spinning around. And he deduced this by going back and looking at um, previous records of the precession of the stars. Obviously, those records don't exist anymore, but he was able to have access to that. And he also, in addition to making this discovery, prepared a stellar catalog that was used by individuals later on. So here are the dimensions that Aristarchus came up with. And you can see when he calculates, for example, the Earth Moon distance down here on the third line, he's off by a factor of three, and even more so with the Earth Sun distance. But, that's not bad, considering what he had to work with. He was doing all these observations naked eye. Any kind of instruments that he was using were very crude. So the fact that he got that close, I thought was pretty amazing. He actually got really close with the Earth's radius, or the Earth radius and moon radii. You can see here 0.285 versus 0.367. So while he didn't have the accuracy that we're accustomed to today, he certainly set us off in the right direction and made some measurements that I thought were pretty astounding. Okay, so now what we're going to do is we're going to pivot. We just talked about ancient Greece. We're now moving into the latter part of the Roman Empire, which you can see here on the timeline, fell around 476 AD. We'll start out with the geocentric model perfected and then talk about the heliocentric model. Um, there's some comments I want to make on this before we go to the details. And you'll notice that the geocentric model is a period of time that lasts from 100 to 1500 AD. So that's 1400 years. And you might think, wow, that's amazing. There must have been a lot of work going on with the model during that time. And there really wasn't. It was one person, Ptolemy, that put the model together and left a lasting record that lasted over a millennium. So that's why you see such a long period of time here. When we get to the Renaissance, which you see here at 1500 and roughly 1600 AD, that's when you begin to see a return to the critical thinking that we saw during ancient Greece. And there you see some thinking that went into upending the geocentric model. But more about that in a second. So, let's talk about Ptolemy. Ptolemy was a Greek by lineage, but he lived in ancient Egypt and in Alexandria to be exact. And Romans actually had taken over ancient Egypt by that time. Cleopatra had been deposed, and Romans moved in and took over. So the thing that I want to talk to you about with respect to Ptolemy was, first of all, Ptolemy was an astrologer, so he was very interested in understanding the position of the planets at all times. And in order to get there, he had a big hurdle to climb, and that was to model and understand retrograde motion of the planets. And here's what he did in order to achieve that. He came up with these devices that are called an epicycle, which is a small circle that a planet T here rotates around while the center of the epicycle is following this circular path that you see here, which you could think of as the kind of the main orbit, if you will. Here's the Earth, right here is Tau, and when he put this together, he actually went ahead and made an offset here of the Earth from the centroid of the deferent, which is the circular orbit here. So this is actually the center of the circle with Earth down here, and then the planet and the epicycle rotating in the pathway here. He added an additional offset called an equant, and here you see the line of the equant going out to the center of the epicycle. And what the effect of this offset was is to give the orbit of the planet a more elliptical path. And he needed to do that in order to get the path that he observed up in the sky to match his model. Um, and then you see down here in this last uh, piece of the diagram, the retrograde motion that is modeled here. And if you remember, the retrograde motion is, as we now know, we're in a heliocentric model. When the Earth is on the inside track and say Mars or Jupiter is on that outside track, the retrograde motion occurs when we actually pass going around the sun on that inside track. We pass the position of the outer planet. So that's what Ptolemy was attempting to do, and he was able to do that uh, relatively effectively with this model. My explanation, I believe, is correct. Although, if somebody finds that I've stated something in error, please point that out. I did my best to research this and really get a handle on it, but sometimes you don't always get there. So this was the geocentric model perfected. I think what he did, at least in my opinion, what he did that I think is much more important is he left a lasting written record of um, of its work in a document called Almagast, and in it he recorded astronomical information about the movement of the sun, moon, five planets, and fixed stars. It was broken up into 13 books, and it was based partly on Hipparchus's stellar catalog. So that was the real contribution because while his model may have been flawed, he left a written record of what did so that others that came after him could use that and really get to the right um, right understanding. Okay. So that was Ptolemy and the geocentric model perfected. When we moved into the Renaissance, we moved into a period of time, and again, this is 1300 or roughly 1600. We ran into a period of time that was marked by a critical thinking, and the astronomers of the day had a real dissatisfaction with the geocentric model, and it was a useful model, but in their minds, in the astronomers' minds, it just didn't describe reality. And so that's what people like Nicholas Copernicus, Galileo, and Johannes Kepler were really trying to drive at. You know, what is really happening out in the cosmos? Um, Copernicus, a little bit about these individuals. He was Polish, but did his lion's share of his astronomical work done in Bologna, Italy. Galileo was Italian and did his work in Padilla. And Johannes Kepler, um, he was did his work in Prague, which is in modern day Czech Republic. So, what did these individuals contribute to our understanding of the cosmos? Here you see in the upper left the Copernicus uh, contribution. Essentially, he proposed that we live in a heliocentric world as opposed to a geocentric world. Um, and it was a very elegant solution by making that change in our assumptions because no longer did you need these epicycles or equants or anything like that. You were able to more straightforwardly predict the motion of the planets. Um, Doing so during this period of time was a little bit tricky, a little bit dicey because the church had a vested interest in the geocentric and geocentricity, generally speaking, uh, because man was at the center of the world, of the universe, and the earth would be at the center of the solar system. So, saying something to the effect that we, rotate around the sun could get you in trouble. Um, Copernicus actually, when he published his treatise on his model called De Revolutionibus, which was published about 2 months prior to his death, there was actually a kind of a disclaimer in that document that said, "Hey, um, this is a model. It helps us to predict the position of the planets, but it's not necessarily what's really happening." I don't know if that was done um, by him or his or the underlings that worked for him as a kind of a protective thing, but it was in the document. And uh, given the fact that this was published 2 months before his death, it kind of in addition gave Copernicus an out, so to speak, so as not to run afoul of the authorities. So that was Copernicus. He had, and in his model, he assumed circular orbits, which is kind of important. We'll get back to that in a second. Galileo, I think he's pretty well known, understood. He was the first astronomer to make observations using a telescope, and he added credence and evidence to the heliocentric model by his observations of the four largest moons of Jupiter. And you see the picture that you see on the screen here is a picture of Jupiter, and over here on the right, you can see one of Jupiter's moons and the shadow of the moon crossing and transiting in front of Jupiter. These observations directly challenged the geocentric model because now something was not orbiting the Earth; it was orbiting another body. So that was a key finding and support of the heliocentric model. It got him in trouble, and he ran afoul of the church authorities during this time for these findings. Um, he negotiated around them as best he could, but I think there were periods of time where he was arrested and confined. So that was Galileo. The third person that in the Renaissance time that really contributed was Kepler. Kepler kind of, in my opinion, he kind of added some meat and some numbers and calculations to the whole question of orbits of the planet around the sun. He came up with Kepler's three laws, and the first law being that orbits are elliptical, and that in its second law, equal areas are swept out during equal time. So, in this little diagram that you see down here, this sector of the ellipse is equal in area to this sector right here. And so that was his second law. And then his third law was to provide a mathematical relationship between the time to complete an orbit and the semi-major axis, which is denoted by A right down here. And it's kind of a t squared is proportional to a cubed relationship. Um, this is important, I think, because if you really begin to see the use of quantitative science like math um, employed to describe and predict orbits. These laws also explain the orbital speed variations of Mars. So um, that was another uh, uh, key predictor or key thing about Kepler's laws that made them valuable. And again, they kind of set the stage for our next period of time, which we'll jump to right now. And this was kinematic to dynamic. And here is where we'll talk about again Robert Hooke and Isaac Newton, and then we'll talk about a broader cosmos and the contributions of William Herschel. So let's jump into it with Robert Hooke and Isaac Newton. So again, as there was in the Renaissance, there was a dissatisfaction with the geocentric model um, because it didn't in the minds of the Renaissance thinkers, it didn't predict or didn't explain reality. There was a further dissatisfaction when we get into this period of time with the divinely inspired orbital paths. Yes, orbital paths were elliptical. It's described by Kepler and Copernicus, or circular in the case of Copernicus. But the big question is, well, why, in fact, do the Earth, Moon, and the planets follow their orbits? What is the underlying reason for that? And that's what this period of time is all about. So when I was doing research for this presentation, Robert Hooke was somebody that I had really never heard of before. Um, and he was in my opinion, was important in this story because he showed that a central force leads to orbital motion. He didn't quantify it, but he did make that supposition. And Isaac Newton uh, eventually incorporated that and was able to describe what Hooke was talking about in very quantitative terms with his with Newton's laws. So that I think is a key thing, and I'll get into more details here. Robert Hooke studied pendulum motion, and while he didn't directly use the pendulum motions to formulate his theory of orbital motion. It did influence his thinking. It provided him kind of um, a thought, mental model for how this ought to work. Um, and so, uh, when you hear about Robert Hooke and you hear about his study of pendulums, that's what it's related to. And so, with that, let's talk about what Robert Hooke actually did. So here you see a pretty complicated diagram, and the quote up at the top, I'm just going to read to you because I think it does the best job of any in describing what Hooke was thinking. And what he was saying here is that the orbital motion of a planet is determined by compounding its tangential velocity, which you see right here in segment B and G, and that, uh, with the radial velocity, which is down here represented by this segment, G and C, and that compounding is impressed by the gravitational attraction of the sun. So in this, what he's referring to here, in this case, N would be the sun. What he's trying to do is he's trying to conceptualize um, why. things orbit. And this is the explanation and the thinking that he came up with that was eventually incorporated into Newton's laws. When we talk about Isaac Newton, we're talking about somebody here that had a profound impact not only on astronomy but on physics in general. Um, I like to think of myself, I was a mechanical engineer for an oil company for 34 years, and during that period of time, I was either applying or dealing with or working against Newton's laws almost on a daily basis. And what Newton's laws are uh, is as follows. His first law was that every object moves in a straight line unless acted upon by a force. His second law, which is really, I think, is the most important one here, is that the acceleration of an object is directly proportional to the net force exerted and inversely proportional to the mass of the object. So what he was able to do here is he was able to go beyond description of motion, like Kepler and like the Renaissance astronomers were doing, and really describe the cause of the motion. And that was kind of the big contribution that he made here. This law connects mass with weight and applies to many standard problems, not only problems out in the cosmos in orbital motion, but also many problems here on Earth. And it dealt with frictional forces as well. If we get over to this part of the diagram, we can see here that the forces in circular motion and forces of gravity are also dealt with by Newton's second law. The third law, which I'll just mention, is for every action, there's an equal and opposite reaction. And that's what you'll see out of the branch here. But it's really around Newton's second law that you see the connection with uh, Newton's work with astronomy. So to bring it all together, and before we bring it all together, uh, a couple of more things about Newton. He actually made some fundamental discoveries in optics. He invented a differential and integral calculus to help him quantify um, his laws, and he published in 1686 a document called Principia describing the discovery of gravity and motion and orbits of planets. So that's what we have here with Newton's laws. So how did they all come together? Um, and again, I'm going to read this passage because I think the text that I've got up here describes it best. Um, but let me just indulge me for a second. So here we see Hooke proposed the idea that celestial bodies such as planets were held in their orbits around the sun by a force proportional to the square of the distance between them. And that square of the distance is important. Newton formulated his laws of universal gravitation, stating that every particle of matter in the universe attracts every other particle of matter, every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of their distances. So we got that square of distance feature that you see up in that third bullet. So this law provided a fundamental or mathematical framework for understanding not only terrestrial motion, but also the motion of celestial bodies. And Newton's three laws, especially his first law and second law, provided a theoretical foundation for understanding how objects move under the influence of gravitational forces, including orbital motion. So here's where the tie between the two happens. I'd be lying to you if I could, um, walk through the details of all this. But I think the key thing to latch onto here is that square distance connection and also the orbital motion thinking that Hooke had in mind. And this is what connects what Newton did to the outer cosmos. And it's, in my opinion, it's a very important contribution because it got down further into describing, why these objects are following an orbital path. Okay, so now we're going to go to a section of the timeline I like to refer to as a broader cosmos. if you notice, really up until this point in time, the uh, the outer sphere of six stars, as Pythagoras said, were really um, uh, little interest other than they were there and they could help um, in understanding the changes of the season. But there wasn't really anything going on out there per se. Um, every once in a while, there would be an event out in in the broader cosmos that would occur, such as the Crab Nebula that was observed by Chinese astronomers. I think somewhere in the neighborhood of 1200. Don't go check me on my dates, but um, that was one example where something in the broader cosmos happened, but there was really nothing that was really methodically undertaken to really better understand the outer cosmos until William Herschel came along. And this astronomer was exceptional. Typically, an astronomer would be a good astronomer will be a great theorist or a great observer or a great builder. Rarely are they two of these three, and almost never are they all three. And William Herschel certainly was. And you can see if he's going to be going out and really describing the outer cosmos in more detail, his his uh, his abilities as a builder and observer are key. So what did he do? So just as a builder, he constructed 73 telescopes in its lifetime. He fabricated over 400 mirrors of various sizes, performed and recorded about 2,200 experiments on telescope construction. And he constructed and delivered telescopes for royalty and dignitaries throughout Europe. So um, I don't know if you remember, saw on the timeline, the Napoleonic Wars were actually occurring. Let me just see if I can flip back up to that quickly. The Napoleonic Wars were happening here in the latter part of this period of time. And William Herschel actually delivered a telescope, one that he had built to Napoleon's brother. So, kings, queens, noblemen of all stripes throughout Europe commissioned and received telescopes from that were built by William Herschel. As an observer, he was extremely productive. His discoveries were important in that they, got him in the door, so to speak, which in this case was his discovery of Uranus, the planet Uranus. That was the first planet discovered since antiquity, so that was a big deal. He also discovered infrared light, and he also discovered that the solar system is moving towards Lambda Hercules, which is a star near Vega. So, amazing discoveries. His observations of planetary motion of the sun, the moon, and the planets were remarkable. He was able to calculate mountain heights given his, using his observations of mountains on the moon. He discovered that Mars had an atmosphere. I mean, the list goes on and on. Where he really begins to get outside of the solar system is when he published these next three documents. So, in the observation of periodic stars, he begins to observe that there are stars out there that actually have a period of brightening and dimming. He records the minimum and maximum brightening that he sees on these stars, and he's beginning to put together a theory about what that's all about. He stated here in one of his documents that maybe there is a small sun rotating around a rather large opaque object. He also theorized that perhaps sunspots were the cause of the dimming. Um, and so he had these two in mind, but as you can tell, when he gets into the review of the heavens, he really focuses in on binary stars. He documented about 806 new binary stars. Uh, Most of the double stars at the same distance. Early thinking was that if a star was really bright, it was close, and if it was dim, it was very far away from Earth. He deduced through his observations of of brightening and dimming, that these stars were actually circling each other, and that the stars were of different brightness and were more they were closer to each other than they obviously were to, one that the bright star being closer to Earth. So it's really beginning to hone in on that. And by extension, you can see where he's beginning to touch on the fact that gravity extends beyond the solar system. I know Newton stated that in its laws of in his laws of physics. Um, but the observation that Herschel made of binary stars really adds credence to that. In the catalog of new nebulae and star clusters, he did some remarkable work. He cataloged about 2,500 objects, only 138 of which had been previously discovered. So we're talking about nebulae, star clusters, globular clusters, you name it. And again, he's really expanding our view and our understanding of the broader cosmos. So that's what he did as an observer. And then when we get into the period of time where he is what I call as a theorist, he's really beginning to uh, break the doors down in terms of understanding the broader universe. So what you see here in his document or papers on the construction of the heavens, he's actually worked to map out the Milky Way. He was able to determine the correct shape. It was a disk and a bulge. The sun was in the galactic plane and the sun is offset from the center. And these were deductions that he was making from a technique called gauging, where he would look out in a certain field of view and document the density of the stars. So from those observations, he was able to map the Milky Way. And it was at this point in time he suspected that not all nebulae are star clusters. He thought that if he had a powerful enough telescope, he could resolve individual star clusters from nebulosity. A good case in point was M13, I think the Hercules Nebulae or globular cluster, excuse me, where Messier had uh, originally documented that as kind of a fuzzy, almost nebulous-looking cloud. Whereas when Herschel went out, he actually was able to resolve it into individual stars with his one of his high-powered telescopes. But he reached a point, and it's you see down here in his another paper he wrote called "On Nebulous Stars." He reached a point where he began to question that. Um, in earnest. There was a planetary nebula called NGC 1514, and it was a single star surrounded by an atmosphere, and he couldn't quite sort it out in his mind. And he came to the conclusion eventually that there really must be objects that are true nebulae. Okay, so really beginning to touch on a key thing here. Um, when he talks about the nature of shining light, he's asking questions. Is the central point is the central point, is that a star forming out of the fluid, or is gravity working on the luminous matter? So he's really beginning to touch in a big way on the life cycle of a star. And this final statement that he has down here, and stars forming these extraordinary nebulae by some waste of nature will no longer fit with a form of purpose, and they unite into the new body. Well, here you're talking about, what we talk about today when we think about the death of a star, planetary nebula, white dwarfs, supernova that would result in a neutron star or black hole. So, really beginning to touch on some key points, and then he kind of brings it home in his document called The Construction of the Heavens, where he really lays out the foundation of modern physics, astrophysics. Um, he also states that nebulae are not permanent bodies. By comparing his drawings to what preceded him in terms of like the Orion Nebula, he can see that there's change actually occurring. And then he also makes this statement, which really begins to set us on a path for where we're at today, which is stars going through a life history. Now, he didn't quite have it right. He talks about the universe uh, beginning with widely separated stars. It's probably not a um, bad statement. And then those slowly condensing into large agglomerates like the Milky Way. Again, that could be on the right track. they condense further into globular clusters. I think that's where we begin to part ways with them here, and that the globular cluster evolved into planetary nebula, which in fact could individual stars certainly could. The last thing he says down here really kind of hits home, though, and that is nebulae are the parents of stars, and a new star is formed, and the process repeats. So that's really, I think, where he really sets the foundation for modern astrophysics. Truly remarkable individual. Okay, so moving along, we're now going to hit on a time period that runs from 1830 to 1930 um, that I call a new understanding of physics on a broader universe. Um, and this is remarkable stuff here as well. I'm still trying to get my mind wrapped around everything. Now, Albert Einstein and Edwin Hubble are going to be who we'll really focus on here, but I did want to give an honorable mention to an individual by the name of William Huggins. In 1862, he identified chemical elements in stars and said that the dark lines in their spectra matched the wavelengths of atoms measured in laboratories. So, you know, we had Newton looking at optic, splitting up the starlight or sunlight coming in into the different colors of the spectrum. Um, you had Herschel, who was actually doing this as well with stars other than our sun, but they really weren't making the connection here. And I wanted to mention this guy because spectroscopy, which is really what this is all about, is such a common, pervasive tool in astronomy and astrophysics that, I think this guy deserves a little credit for that. So there you have it, William Huggins. Now let's talk about Albert Einstein and Edwin Hubble. These two individuals um, were located, well, Edwin Hubble started out in Europe, spent time in Switzerland, Germany, and then eventually came to the US. It was during his time in Switzerland that he actually uh, developed his general theory of relativity. And then Edwin Hubble was a person that was at the same time period located here in the United States. So Einstein was an amazing person. He did all of the theorizing using thought experiments, which I find remarkable. And what he came up with in his general theory of relativity was uh, just unbelievable things. And it's just to kind of give you a rundown. The general theory of relativity um, states that matter curves space, and that's causing bodies to move in a way that's attributable to gravity. So that's what you see happening up here. Rather than having this invisible attraction between the Earth and the Sun, as described by Hooke and Isaac Newton, he's actually describing this deformation of space time, and that being the source of the attraction between planets and the sun, and really just about everything else. Um, his general theory of relativity, which he developed or published, I think, in 1916, it predicted black holes, gravitational waves, gravitational lensing, and the expansion of the universe and time dilation. So again, it's an amazing set of findings or amazing set of postulations. So here's gravitational lensing, and this was actually proved out in a solar eclipse, I think during or maybe just after World War One. And people had to pull together a lot of equipment, travel to Africa to make these observations. But this was, I think, the test that they actually performed. You had these two stars out here, and on a straight line, the sun would have been in between those stars, so you wouldn't be able to see them. And obviously, with the sunlight um, shining, you wouldn't be able to see them anyway. But when they had the eclipse, it darkened the sky to the point where they were actually able to see stars in general and see these two stars in particular. And what was happening here is that the starlight from these stars is actually bent around the fabric of space-time due to the gravitational or the mass that the sun that you see right here. And so that prediction was actually proved out during an eclipse. And again, quite remarkable. Black holes are really a manifestation of the curvature of space-time and an extreme example. This is where you have an object that is so heavy, so massive that starlight can't even escape from uh, the indention or the stretching of space-time, the fabric of space-time. So that was another prediction, and then gravity waves was another prediction from general theory of relativity. And here we actually observed it for the first time in 2015 with the LIGO Observatory. So that's Albert Einstein in general theory of relativity. We'll talk about Edwin Hubble. I think he did a couple of really important things to drive us forward into the 20th century. His work with sifted variables really showed that there was a universe beyond the Milky Way. Everybody had originally thought that Andromeda was a nearby nebula, and again, with Hubble's work, he was able to show that this galaxy is really kind of its own island universe, separate from the Milky Way, and it really led to the concept of broader understanding of a much broader universe than what people had thought about up to that point in time. Here in 1929, uh, he was able to confirm Einstein's uh, expansion of the universe prediction from general relativity with his observations and development of the Hubble constant, um, and that was an important contribution as well. The one thing I want to go back to a little bit on this whole idea of an expanding universe. Um, in Einstein's relativity equations, the space-time containing matter cannot remain stationary and must either expand or contract. So there's something like a galaxy. They're not strictly expanding away from each other, but they're rather attached to the fixed grid of an expanding fabric of space-time. So I've always thought about objects like our galaxy moving or having, when we observe galaxies moving away from us, that they're, actually points out in a vacuum. And what Einstein's arguing here is that we're, all the what's happening is rather than the object moving independently, you've got the fabric of space time expanding. So I'm still trying to figure that one out. So if you've got questions on that, I'll do my best, but I can't promise you anything. So anyway, those are Einstein and Hubble, and I wanted to kind of wrap up the discussion of these guys because the uh, the thing about what those two individuals came up with, they really set the stage for what we've been looking or doing, researching over the last 100 years. Just kind of take the few key things here. Gravitational lensing, that's been used to study distant galaxies and even detect exoplanets because now you can see something that's behind a massive object like a giant galaxy. Black holes went from a mathematical abstraction to an observed and studied object, a phenomenon across the universe. Gravitational waves has opened up a new era of astronomy and offered a new way to study cosmic phenomena. And then, just generally speaking, with respect to cosmology, Einstein and Hubble laid the groundwork for the Big Bang theory and our understanding of cosmic expansion. So, um, that again, I think this period of time and these two individuals in particular, not just these two individuals, but two individuals that I picked out that I thought were really at the center of all this, really kind of set the stage for the last 100 years. So with that, we'll move into our last period of time here. Talk about exploration and discovery accelerated, which takes us from 1930 up to the present. Um, there are a number of astronomers out there over the last 100 years. Picking four of these was, real crapshoot. But here are four that caught my eye. uh, Sabra, Sabramen, uh, Subramanian Chandrasekhar. Say that three times fast. He was an Indian astronomer who came up with Chandra's limit, which is 1.4 times the mass of the sun. Anything heavier would turn into a neutron star or black hole upon the end of its life. Anything under would turn into a white dwarf and a planetary nebula. Uh, Earl Rubin provided evidence for the existence of dark matter through observations of galaxy rotation curves. Stephen Hawking made a theoretical prediction that black holes emit radiation, and then Jocelyn Bell Burnell co-discovered pulsars that really revolutionized our understanding of neutron stars. So, four out of a whole host of people, four that I thought were pretty interesting, four that I just wanted to share with you for this presentation. Now, when we talk about accomplishments, there's just so many to talk about. So I'm going to kind of glide over these a little bit briefly. Um, the space age, I think, was a really key turning point. We had Sputnik that went up in 1957. Since that period of time, many uh, manned and unmanned missions have been sent out into space. The Mariner program, which sent probes to all the planets. We had Apollo, which is a manned mission to the moon. Gathered a lot of geologic information about the moon. We sent Viking and other missions to Mars. Of course, we've had Voyager, which is really even still going here. It's gone past the four outer planets and now is going beyond our solar system. Um, so a lot of activity, Juno, Cassini, other probes that have been out there, um, really, really opened up the door for us to really get our hands on um, and really do some quantitative discovery out in our solar system. The cosmic background, microwave background radiation was discovered in 65, and this provided strong evidence of the Big Bang theory of the universe's origin. 1990, we had Hubble that went up, and that really kind of set the stage and the bar for looking into the heavens. Um, Last year, I made a presentation on space observatories. We currently have about 40 to 45 up in space right now, with another 34 to come. So, in addition to Hubble, you've had James Webb, Gaia, Solar Dynamic Observatory. There's just more than you can shake a stick at. Exoplanet discoveries. Um, the discovery of the first exoplanet was in 1992, and that's just opened up a whole field of astronomy and dedicated to studying planets outside our solar system. And literally have thousands of exoplanets that have been discovered since that period of time. Dark energy and dark matter, kind of a the big area of inquiry in astronomy and astrophysics. Um, Large scale structure and the cosmic microwave background have let us realize that the majority of the universe consists of something called dark energy and dark matter, and it's very poorly understood. So there's a lot of effort going into better understand what's going on there. And then gravitational wave observations by LIGO back in 2015 that I mentioned earlier. So these are just a sampling of the accomplishments, achievements that we've achieved over the last 100 years. I just want to quickly wrap up and talk about what's coming up next. There's a document called Astro 2020, which kind of serves as a roadmap for uh, astrophysical and astronomical research. And here are kind of the five areas that they've outlined. With exoplanets, they're going to be doing more analysis of atmospheres and also begin to look at the protoplanets and understand how those solar systems are forming. A lot of questions around that. This topic called new messengers is really about incorporating things like gravity waves and neutrino observation into the uh, the light data that's collected on a phenomena bringing all that together to get a better, more comprehensive picture, or more comprehensive set of data on exactly what's going on. With respect to the dynamic universe here, they're looking for, uh, you know, big events like two black holes merging, supernovas, things like that, using ground-based telescopes to gather light on those events. And then again, there's also work to develop a next generation of radio telescope to detect things like relativistic jets that are produced by neutron stars and black holes. The cosmic ecosystem category, we're talking about looking back in time. So Webb has been starting out and beginning to peer back into the early stages of galaxy formation and evolution. And then as those discoveries are made, ground-based telescopes kind of pick up uh, the the ball from there and really study. This last area, drivers of galaxy growth, this is looking at the younger universe. So using our ground-based telescopes to look at the young universe, and there are also some space telescopes that are on the drawing board to go up and um, go out into space and look at the details in um, more granular form. So a little bit about what's coming up, and with that, I'll wrap up because I think we're running a little late, but I gave a heads up on that. So to quickly go through this, we start out with ancient civilizations using astronomy for practical and mystical purposes. Greek philosophers brought rational thought to our understanding of the heavens by attempting to describe the nature and size of our solar system. Ptolemy perfected the geocentric model in order to provide accurate positions of the moon, sun, and the planets, and he left a lasting written record of his work. Renaissance astronomers like Copernicus, Galileo, and Kepler upended and replaced the geocentric model with the heliocentric model. Newton, with some help from Robert Hooke, provided a quantitative and predictive explanation for gravity and orbital motion. Uh, William Herschel laid the foundation for modern cosmology by unveiling a broader cosmos and by laying out the nature and relationship between stars and nebulae. The general theory of relativity provided a new understanding of physics and, together with contributions by Herschel and Hubble, in my opinion, set the stage for astronomical inquiry over the last 100 years. During 2020 and 2030, these areas of inquiry will be further developed and expanded. And that's what I have with the presentation. I just want to give one big shout out to Larry Mitchell. His presentation on Sir William Herschel, who he presented to both FBAC and the HAS, is outstanding. I drew a lot on that. I won't go through each of these references because we're running out of time. But if you're interested, shoot me a note at chrism@astronomyhouston.org and I'll get the information to you. Just before we get into questions, if you can, please join us tomorrow night. Debbie Moran will be presenting responsible night lighting advocacy. And so that's that. And with that, I thank you. And with that, we can begin to go to any questions that anybody may have. So let me pull that up. This is the first one here by Tumaj Arzira. Per Kepler's law, the Earth moves faster when it's closer to the sun and slower when it is further. That means Earth has accelerated movement. Did we not sense the acceleration? Um, I wouldn't think so because we are on our frame of reference is so um, big. In other words, I mean, we're out on this big, huge sphere called Earth. I think you can sense it by um, looking at planetary and star uh, positions, but just physically sensing it. Um, I don't think. I don't think. I don't think you could. So, did you have anything did I answer your question, or did you have anything else you wanted to add there, Homage? Or anybody there?
I speak.
Yes.
Hey, hello. This is too much. I'm also mechanical engineer. I'm also working in oil and gas companies. I was thinking per Newton's second law, F is equal to M multiplied by A. F is equal to MA. So
Okay.
if we have an accelerated movement, then I think I know we don't sense anything, but I think we should sense force that F is equal to ma. So if it was a constant speed, then okay, everything is fine.
Mhm.
Everything was fine. We shouldn't sense anything. But since it accelerated, I don't know how we couldn't sense the force.
Well, you may be able to sense it if there's instrumentation that is that is set up and can measure that delta. But I'll be honest with you, just off the top of my head, I don't have a
Chris,
satisfactory answer. Yes, sir.
and Tomasz, the answer to his question has to do with general relativity. It's because an inertial frame, which is a frame of reference where you don't feel acceleration, general relativity explains to us that the gravity is causing the inertial reference frame to curve. And that's why you don't feel any acceleration. It's because gravity has warped it. That probably that may not be understandable, but the answer to the question has to do with general relativity.
Something that I will definitely follow up on because you've got me interested now. So, yes, thank you. That was Mark, correct?
Correct.
Yes, thank you, Mark. Um, I got another question here from who is it from? Brooke Marshall. Great presentation, but surprised there wasn't any mention of Tycho Brahe, Charles Messier, and Henrietta Swan Leavitt. Yes. So let me talk about Brahe. He did, in fact, provide information that was key to what Kepler did in coming up with his laws of motion. Um, but uh, I didn't see that as necessarily a breakthrough. And again, keep in mind that I'm talking about, the history of astronomy for the last 5,000 years, and I had to cram it into an hour. So, there are some things that'll probably get not covered. Hopefully, I've motivated you to study some of the others. But Tycho, I did think about him, but I didn't include him because, again, uh, his observations were helpful, but there wasn't anything um, revolutionary. And then he also, I think, still hung on to the geocentric model as his operating uh, model of how the universe really works. So that's why I didn't include Tycho. Charles Messier, he is a beloved guy by every astronomer in the world. He came up with just a wonderful catalog of objects. But here again, his catalog, while it covers some real highlights, was very incomplete. Um, he has over roughly 100 plus objects in his catalog. Compare that to what Herschel did in observing and coming up with, over 2,500. Um, I just didn't see the same level of contribution there from Messier as I saw from Herschel. And Messier also was looking at objects um, as things that were not comets. So there wasn't his catalog and this may not be fair, and I hope it's not. I hope I'm not sounding like I'm being unfair to Messier, but it didn't sound like he was intentionally going out and discovering, like I saw with Virgil. He was more collecting things that weren't of interest to him, and wanted to make sure that people who were looking for comets, didn't mistake these objects that he collected for comets. So that's why he wasn't included. Um, Henrietta Swan Leavitt. Um, yeah, again, don't know much about her. Um, and I think it's fair to say that, yeah, I probably should have taken a look at that. But again, just given the time constraints that I had to really kind of narrow things down. So that's why I didn't include uh, any information about those three. So did that address your concerns, Brooke, or did you have anything else you wanted to ask or say? Mm.
No, that was good.
Okay, real good. All right. I don't see anything else in the chat. If somebody does have a question, feel free to come off of mute and ask your question if you'd like.
Hey, Chris, it's Chris Shoemake. Can you hear me?
I can, yes.
Yeah, excellent presentation as usual. Well thought out, well researched, and well presented. So thank you for your continued efforts for us. I have a just a kind of a crystal ball question.
Okay.
As you look in your crystal ball and you look at the Astro 2020 information with those five different focus points, exoplanets, new messengers, et cetera, those. Do you have any kind of thoughts about what you think we'll see over the next 10, 20 years or so? Will be, true breakthroughs. It seems like information and awareness is obviously increasing at an increasing rate. We're learning a lot, seeing a lot of it, a lot of things going on. All those observatories in space you mentioned earlier. But what do you think is going to kind of come down the road? What do you think is going to surprise us?
Well, that's a that's a really good question. Um,
It's a little broad too. I'm sorry
uh,
about that. But
no,
it's-
that's fair. I think just off the top of my head, I really owe you a better explanation. I think this whole issue, uh, uh, topic of dark matter and dark energy. I'm hopeful that something really gets sorted out and that we really get a handle on it. Right now, it's as I said earlier, it's not poorly understood, and it's quite possible. I don't want to. I'm not throwing this out as anything like I'm any great scientist or anything. It's quite possible that there is no such thing as dark energy or dark matter, and the laws of gravity are actually different in some places in the universe. So, you know, that could be a possible explanation, but I think there's got to be. I'm hopeful that there are some breakthroughs there that really help us uh, get a handle around that because you're talking about material that is 60, 70% of the universe and we don't understand it. So, there's that. I think the exoplanet one's pretty interesting. Wouldn't be surprised if they find, atmospheres out there that are uh, capable of supporting life as we would recognize it. Um, and then the other one that, as I was researching this, was kind of intriguing was the whole new messengers thing. We discovered gravity waves, which is great, uh, but um, but we haven't really incorporated those into our understanding of dynamic phenomena. To use that as another measurement, if you will, along with light and neutrinos as well. So I know they've got this one uh, uh, called LISA, called a laser interferometer space antenna, and it actually is three pods that are out in space that beam a laser between each of the three, kind of like what you've got with the LIGO Observatory, and they're going to be using that to detect gravity waves at lower frequencies that would be what you would expect to see. I think when two supermassive black holes get close to each other and combine. So, think hopefully, gravity waves can be incorporated into our understanding of phenomena out in space. But I think again, the dark matter, the question is is the thing that I hope we get some breakthroughs on
Great response. Thank you very much.
that. Anybody else? All right. Well, listen. Let me do. Mark. It was Mark Gordon. I think you said you had the comments about the first question here. I appreciate you chiming in. You get so wrapped up in these presentations, sometimes you lose the forest before the trees. So sometimes I get my head. I want to hit the script right, and I have a hard time taking a step back and thinking about things. So I appreciate your comments there. And I'll tell you what, unless anybody has anything else, I think we're done for the evening. Again, I really appreciate everybody coming in and sticking with me past the 8 o'clock hour. And I hope y'all are able to make it tomorrow for Debbie's talk and wish you a pleasant evening. Thank you.